See, this lesson's titled Equipotential Surfaces and E as a Slope. And so the first thing we want to do is just kind of think about what we understand the relationship between potential, so voltage, and electric field to be right now. And our big kind of go-to idea is that V is equal to the negative integral of E dot dl or just E dr when we're looking at those two things being parallel to each other. Okay. What we can see in that piece, and this is kind of the mildly confusing thing, V is the sum of all these little EDRs. So in my mind, I kind of think of this as being little tiny dVs. Now, whether that's right, wrong, or otherwise, that's just kind of how I think about it. But what I'm trying to say with this, I guess, is maybe like this is how some mathematicians would do it. At least I had a professor in college who did it. He would say, well, if we take the derivative of both of these sides, the derivative of V is dV, and derivatives undo integrals. And so he would just write things like this. It's a little bit mathematically stretching it, but it works. And it pretty much works all the time, so I kind of roll with it. And then he would kind of say that this was true, that dV by dr, negative, was equal to E. Okay, what that's arguing is that electric field is actually a slope. Now, it's a negative slope, but it's looking at the rate of change of voltage with respect to position. So if you're looking at electric field strength, the more rapidly you're changing your voltage with respect to each little change in position, the stronger your electric field is. Okay, that's what that's arguing. Okay, that's kind of one idea. It's just E as a slope. So I don't know why I wrote it second and then talked about it first, but that's an idea. Okay, the second thing on our list is equipotential surfaces. So, and I guess I should say equipotential lines. Well, an equipotential line or an equipotential surface is exactly what it sounds like. So, equipotential sounds like equal potential. That's exactly what it is. These are lines or surfaces where V, the voltage, the potential, is constant at all points on that line or surface. Okay? So it's just kind of a way to say, hey, everything along this line is at a constant voltage. Or everything around this surface, if it's like a 3D shape, is at the same voltage. We can draw a couple equipotential lines for some simple charge distributions. So let's start off with the simplest of simple charge distributions, plus Q. Okay, we want to draw an equipotential line. Let's start off with an equipotential line, not a surface, because a line's a lot easier to draw than a surface. So draw what you think an equipotential line would look like for that source charge. And I'm going to pause the video and we'll talk about it afterward. All right, our class came up with the idea that a circle of radius r would be an equipotential line. That makes sense? And then an equipotential line of lower voltage would just be a bigger circle like this. Great. And then we could keep doing this and we just have more and more equipotential lines. So this is a pretty straightforward idea. There's some other things to observe about this, though, that are kind of cool trends. If I was going to draw the electric field lines produced by this positive charge, what direction is the electric field acting? Let's say, like, right here. What direction is the electric field acting? Okay, we said outward. What's the direction of the electric field here? Okay, and we're drawing something like that. And then here it would be like this. Okay. There's something that is not a coincidence. There's two things about this that are not coincidental. The first one is, what do you notice about the direction of E compared to the equipotential line? What do you notice about the orientation of those two things? Okay, they're always perpendicular to each other. So E is always perpendicular to equipotential lines. That's a key idea. That's going to be really helpful here in a second. we'll label that as big idea number 1 out of this brief demonstration. Okay, item number 2. If I label these as loop number 1 and loop number 2, which loop has higher voltage, loop 1 or loop 2? 1. So E also always points from higher to lower potential, which we kind of learned in other portions of this class anyway. E always points from higher to lower potential. And we can test that idea, see if that's true for all charge distributions or just this plus Q. Run that through with a minus Q in your mind. Okay. If we're going to take a look at that minus Q and draw some equipotential lines, we'd be drawing the same shapes. We'd still be drawing circular things here. And if I thought about the direction of E for this picture, E would always be pointing in this way. E would still be perpendicular to the equipotential lines, and as you get closer and closer to this negative charge, is your voltage getting larger or getting smaller? Smaller. It's a more and more negative number. So E still points from higher to lower voltage, always. Okay? So it always points, E always points perpendicular to equipotential lines, and it always points from higher to lower potential. Alright, we're going to pause the video for now, and then we're going to see if we can kind of talk through some other aspects of this. We might come back to the video to add in some other ideas depending on what questions the class asks, but this is about where we're going to pause it first.